All right, so we'll continue with this. So what's the standardization and normalization? So for example, let's say that you have your setup data and you want to be able, you have this random or this perf data. So you can see here, all your data is really sparse out. And what we can do is we can concentrate the data within a range that allows us to be able to uh, much better create a relationship between these values. So what we do is here is when we normalize the data, we want to put the data between 0 and 1. When we standardize the data, we want to be able to set them between -1 and 1. So it's two ways to be able to concentrate your data into a specific range. That's practically what it is. We want to concentrate your data in a specific range. It's either between 0 and 1 or -1 and 1. Standardization would be between -1 and 1. Normalization would be between 0 and 1. And we'll talk about more specifically, right? So normalization again is between 0 and 1. When you take your data from your feature and you turn it into numbers between 0 and 1. So that's what normalization is. The benefit is helpful in certain cases, particularly when calculating the gradient. This is more relevant when working with logistic regression or deep learning. Drawback: outliers get squished and information gets lost. Standardization accounts for outliers much better. So in normalization, outliers can influence your data in a negative way, and so that's the only drawback between normalization. But you can also fix this with standardization. So usually people try normalization first, and then if your data still needs to be fixed, then you do standardization. So here again, in most cases, use normalization versus standardization won't make a big difference. A good rule of thumbs up is try standardization first. Sorry, we standardize first and then we normalize. So models work well. You can use this model. If you try standardization first, the models doesn't work well, then you want to normalize and compare. So gradient-based training, algorithm, logistic regression, and deep learning. So this is the gradient-based training is usually helpful when standardization. Standardization is when you put it between -1 and -1. Normalization is when you change your range between 0 and 1. Regulation is an advanced technique that can be used to combat overfitting for any model described by the equation linear and logistic regression. It does this attempting to shrink the size of the coefficient. So again, regulation is when you actually change, when you shrink the size of your coefficient. You want to make sure that you stay within the range of your data. Reducing overfitting in regression. Regulation is a technique in regression that shrinks the coefficient estimates towards 0, which discourages the development of a more complex model and thus avoids overfitting. Encouraging the models to shrink coefficients can be viewed as a form of built-in feature selection. Regulation significantly reduces the variance of the model without significantly increasing the bias. So let me remind you guys about features and bias. So let's say that you have your data here, and you want your data to be in the center, but normalization. Sorry, let me make this a little bit bigger. So let's say that this is your data, right? Notice that this is very sparse. That is when you have a variation. When you have your data very sparse and not concentrated in a single point, that is variation. Bias, it means that it's supposed to be in the center. So let's say that we have, and your data is supposed to be in the center. If it is in the center, then it is a pretty good bias. But what about if it's all in the outside of your area that you want? So then that's called a bad bias. So variance is how much your data varies. Bias means how off from the target is your values. Types of regulations: rigid regression. A rigid regression, also known as a L2 rigid regression, a penalty term is added to the cost function to introduce a small amount of bias. The penalty term is calculated by multiplying the penalty term by the sum of the square weight of each feature. This is the default of logistic regression. Lasso regression, in lasso regression, also known as L1 regulation, the penalty term includes absolute weights instead of square weights. Since it takes absolute values, it can shrink the coefficient to zero. Lasso regression helps reduce overfitting and perform built-in features. So this is some of the tools that we can use to be able to reduce the overfitting when we train our data. So here's a scenario a scenario problem. It says we are performing a binary classification and want to use the k nearest neighbor model, but don't know what value of k is best. So what can we do? Well, what we can do is we can say, well, let's say we do a 3n model and get a 0.5 accuracy in the test set. And then what we do is we change it and we go back to do a 5n model and get a 0.9 accuracy in the test set. And then we do a 7n model and get a 0.7 accuracy in the test set. So we noticed that as we went through the 5k nearest neighbor, we had our highest value, right? Our highest prediction, accuracy. So what we wanted to do is we said, well, we want to think, well, I think the closer we are to the 5, then the better prediction we're gonna get. So we can here say that we have found a much better optimal k, which is when k equals 5. Here's another scenario. What is the problem? There is a chance that the data leakage will occur during the training process. This means that our test data set has influenced training, even though it's supposed to represent completely unseen data. By using the test set to make decisions about training, we are leaking data from the test set into the training set indirectly. The test set cannot really be trusted anymore as true objective representation of the unseen scene. So what does it mean? What it means is that you have used your trained data, right? And then you tested your data, right? You tested your data and noticed that you were a little bit off. So then you go back and modify your training data or your model to fit your training data, and then you test it again, and then you're like, wait a minute, I think I still need to make some improvements. And so then you go back and train your data, you modify your training data, and then you come back and then you see that you compare it to your validation data, and you notice that you still need to go back and fix it. So you do that again, the whole thing, and now, but the problem here is that you have leaked some data. This model prediction will be now it wouldn't be as complete or as truthful because we kept using our test data to be able to modify our training, which means that we unconditionally have used our test information to be able to train our data. So this is called a leaked data leakage, where we have used relationship of the test to modify our training, and that should not happen. That is bad. So it's kind of like the same thing is like student 1 prepares to a certain way to take a test or exam and gets 50%. Student 2 asks the student 1 what the exam was like, changing how they will prepare for the test, and they get 60%. Student 3 asks student 1 and 2 how was the exam, and changing how they will prepare for the test. So here what we have seen is that the test would not be truthfully to representation of what student number 3 actually knows. Why? Because the student number 3 has studied specifically to do well in the test. And so as we have modified from student 1 to student 2 to student 3, that's what we refer to our hyperparameters. We have modified our hyperparameters to fit the test. And that's what we call data leakage, where we have influenced our model based on the test information, which you should never do. So how can we fix this? Well, there's a way to be able to fix this by creating another section of our data called validation. So we break off a small part of the training data that we will not train with yet. This is called a validation set. Training the model on the remaining part of the training data as usual. So we're still gonna take our training data, we're gonna train it, we're gonna use it to train it, evaluate the model's performance in the validation set. So instead of using our data, our model and testing it on the test, what we do is we use the validation to be able to make sure that we make any adjustment to the hyperparameters. Repeat the process for all possible hyperparameters choices. Train the model on the whole training data set using the best hyperparameter choices you found. So once you determine which one is the best hyperparameter, then you can train your data and then you can actually test it to the actual data. Okay, so that's how this valid area set is gonna prevent it from doing a data leakage. There's multiple ways of doing a validation set. There's one which is called validation, which is practically just take 10% of your data and use it as validation. That's one, the one I just explained. There's another one called the cross validation. It's split the original data set into 80% training and 20% testing. Then you split the training data set into many smaller pieces of folds and train on some of the folds, validate on the rest. So what we do is we break the training data into smaller sections, equally represented data sections. And what we do is we rotate on which one would be your validation, and the rest of them will be your training. And that way we can actually have more options to be able to train our model and validate it. The other one is called the K-fold cross validation, which is very simple to the cross validation. This is a common type of the cross validation CV in which they use K-1 folds for training the one fold validation each time. This means that we train K models overall. So here's the example, the K fold cross validation. So here we have our training data and our testing data. What we do is in this case, we're dividing it into three, where we take one of those sections and use it as the validation, and then the other two as our training. And then we rotate on choosing the validation set until we have finished training it. So we practically have more ways to be able to train our data and have it more effectively without doing data leakage. So validation and a note on the differences uses. So it is important to know that there are two key ways to utilize validation in machine learning. We want to compare different models in hyperparameters, evaluate a single model more rigorously. The process is identical to what we have described so far. The difference is that apply this process only one model with one set of parameters. So we want to make sure that you use one parameter per each model. Report the average and sometimes standard deviation of the validation evaluation metrics on top of the test metrics. Now here we're going to go a little bit over more of the specific code of what we do to be able to feature engineer our data. So scaling, we talked about scaling. We said that there's two types of scaling. There's one that is called normalization and the other one is called standardization. So notice that normalization again is when you set your range between 0 and 1. And standardization is when you change your value between -1 and 1. So we tried this one first, it's standardization, and then we tried normalization. Notice that this is your original data, which is very sparse from each other. And so our goal is to be able to change it into a range between -1 and 1 for the standardization. And if that's still not good enough, then we normalize it to change it between 0 and 1. So here again, the difference between normalization and standardization. Scaling the features is important when compare measurements that have different units and scales. Variables may not contribute equally to the analysis and could create a bias. For example, a variable that ranges between 0 and 100,000 will overweight or outweigh a variable between 0 and 1. Using these variables without applying the scaling techniques will give the larger range a larger weight in the analysis. So that's what I was talking about at the beginning of the lecture, that we want to be able to make sure that we standardize our values so that it can stay within a range, and so that way no feature is going to have more outweigh the value of the other ones just because it is without is the range is way bigger, right? So we want to prevent that. So here's standardization. The standardization formula is the value of the x minus the mu, the average divided by the standard deviation. So again, standardization, it puts the numbers between -1 and 1. And here's how we can standardize our values. So we use from the sklearn preprocess, import the standard scalar. We create an object of it. We create an object called scalar. And we're going to use that scalar to fit our data train. So now this is going to set it between -1 and 1. Now our train data is between 0 and -1 and 1 for all the features. Then we do the same thing for our transform data. So what this is doing is calculating the mean and standard deviation that is going to use the same one for the test, to turn the test data into scale data. We do the same thing with normalization, right? This is the formula for normalization: x minus the minimum of x divided by the max minus the min of x. And again, this is going to set the value between 0 and 1. How we process this is by using the normalization normalizer method. We create this scalar that we're going to use to be able to transform our data from x train to scale train. And then we'd use the same scalar to transform our test data into a x test scale. So we talked about the types of feature engineering. We said that there's 3 types: ordinary encoding, which is for assigning a value, changing the value of the features from an index into a number, and that's usually ideal for when you actually have data that has an order. There's the one-hot encoded, which is practically turning into a binary number with a number of features, and the dummy variable is just the same as hot one encoding, but with one list. How do we encode that in Java? Ordinary encoding would be using a ordinary encoder. Let me go into the next. Sorry, let me pause. Let me create the next video.